All right, so let's go ahead and title our notes water. And we're going to start with just a quick drawing of some water molecules, and we're going to notice how they interact with each other. So just a little refresher, remember that a water molecule begins with an oxygen atom, and then we've got a covalent bond to a hydrogen and another hydrogen over there. Now, remember, though, that the electrons are not shared equally between the hydrogens and the oxygen. Looking at the periodic table, we remember that there's kind of this trend like this direction, kind of a diagonal. As you move more upward and to the right, you become more electronegative. So compared to hydrogen, oxygen is much more electronegative, which means that the cloud of electrons is going to shift more toward the oxygen side, making that side more negative. So we say that this is a negative part of the molecule, and then these two parts are positive. In fact, you know what? Don't do it like that. Go ahead and do it like this. Negative, positive. Okay, so what kind of interaction would this have if it came across another water molecule? Well, what this means is that the next water molecule next to it is going to orient itself like this, where the oxygen is going to connect to the positive side. And then maybe we would have another water molecule over here. But notice that there's kind of the positive side of one water molecule will connect to the negative side of the next water molecule. And so there's an interaction right in here that we want to talk about, and that's called a hydrogen bond. Okay, so a couple things to note about the hydrogen bond. This is an example of water sticking to itself. So when we say that water is sticky, that's kind of what we mean. We mean that it bonds to itself via the hydrogen bonding. Another way of saying this is that these hydrogen bonds are what we call intermolecular bonds. Inter, if you derive the meaning, that means between. So these are the kind of bonds that occur between two different water molecules, a hydrogen bond. Okay, next thing to know about the hydrogen bonds is that they're very weak. Weak bond. Okay, your text gives you this vocab word called cohesion. And cohesion, co means together, right? And so cohesion is referring to the bonding of one water molecule to another. We're going to contrast that with another vocab word, which is called adhesion. And adhesion is when you've got the bonding of one molecule to another type of molecule. So this could be like water molecule bonding to the surface of a leaf, for example. So draw yourself a little leaf here, and then just draw like a water droplets. That's just an example. So water droplets attaching themselves to the surface of a leaf. That's an example of adhesion. So what allows water to bond to itself so well is the fact that water is polar. So we're going to kind of summarize our thoughts here and say that water's polarity is what makes it stick to itself. And have you guys ever seen an insect like walk on water before? Where it's like a little water strider, I think is what they call them, and their legs. So it's really interesting because on the bottom of their legs they have these hydrophobic proteins. And so when they put their little legs down on the water, their little feet actually repel the water. It's kind of like a waterproof jacket. You guys ever seen how like waterproof jackets, the water droplet will land on there, and if it's a really good waterproof jacket, it'll just kind of like roll right off. Like it just rolls right off the jacket. And so there's some kind of hydrophobic molecule that they line those jackets with in order to make it waterproof. Similarly, these water striders, their feet are hydrophobic. And so when they put their legs on the water, their feet don't stick to the water. Their feet actually can kind of walk across the water. I'm trying to think if there's any other examples. You guys ever seen a duck go underwater and then come back up and the water just kind of rolls right off the duck's back? So like ducks, their feathers are lined with kind of a hydrophobic oil to keep them dry as well. There's lots of examples. But one thing I do want to point out is water does have this unique property of forming a surface tension. So if you can picture for a second, I don't know, it almost looks like a film across the top of the water, like a thin veneer, a thin film. And those water striders are like pressing onto it. And it's almost like their feet could break through that film, but they don't. It just kind of stays on the surface. So what that would look like if we zoomed way in on that top layer of the water, where there's kind of this surface tension, what you would see, right, is you'd see this kind of lattice. You'd see a lattice of water molecules. So you'd have like a water molecule here, another water molecule here, and you'd find this kind of alternating pattern, which forms a sort of lattice. Now notice that the reason that these water molecules arrange themselves in such a fashion is that like we said up here, the positive end has to connect to the negative end of the next molecule. So if you wanted to, you could come in here and show us the hydrogen bond in between each one of these water molecules. And I'm going to do that right now. I'm going to add a little dash just to show the hydrogen bonding occurring between each of these molecules. So this hydrogen bonding causes these water molecules to arrange in what we call let's summarize our thoughts here. Hydrogen bonding causes water molecules to form a lattice structure. Which creates a sort of film on water's surface. This is called surface tension. We're going to underline surface tension because that's like one of those phrases that you're going to want to be able to kind of pull out of your back pocket for free response questions. And that's you could use that phrase that water has a surface tension. So today we're going to kind of mess with that surface tension a little bit. And we're going to try to measure it. So just a quick little, well, actually, we got a few more things to say before I talk about the lab. A couple more properties of water. Okay, so polar molecules are hydrophilic, which means, if you break down the etymology of that word, hydro, water, phile or philic means water loving. Okay, so we got polar molecules are hydrophilic, they're water loving, and so they will dissolve in water. So let's go ahead and give a couple examples of that. An example of this would be salts and sugars. If you put salt in water and you stir it, the salt crystal starts to slowly dissolve, and then it becomes part of the solution. Same with sugar. In fact, I did that right up here. We've got some solutions here. This one and this one. I had crystals at the very bottom, but I stirred it in, and those crystals dissolved. Why? Because salt is polar and sugar is polar. However, how would this work if I had put an oil in that water and then stirred the oil? Do you guys think that if I stir that oil enough that oil will eventually dissolve into the water? No, no matter how much you stir an oil, it will always remain separate from the water. And that's an example of non-polar molecules. So non-polar molecules are hydrophobic, hydrophobic, water-fearing, and so they do not dissolve in water. So examples: grease, oil, fat. And by the way, like I gave that example of the duck's feathers. The duck's feathers are actually, they have like a grease or like an oil on them, and that's what makes them waterproof. So if you were to actually look at a salt crystal, so for example, like table salt is an ionic salt, which means you've got a sodium and a chloride, NaCl, and they kind of alternate like this. So if you can picture that crystal there, you've got sodium and chloride next to each other. And the chloride side has a negative charge, and the sodium side has a positive charge. And so if you surround this little salt crystal with water molecules, because water is polar, this negative side of the water molecule will interact with the positive charge on the sodium, and it will attach to it and pull it away from the crystal. And then a water molecule down here, the positive end, will interact with the negative chloride and pull on the ion that way. And pretty soon, as this process repeats, the water molecules just keep coming in and kind of attacking the salt crystal, almost attacking it and pulling it apart. And pretty soon it's just pulled all of those ions apart. And at which point those ions are in solution and dissolved. So it's kind of hard to visualize, but just use your imagination of this process just repeating until the salt crystal is gone. So that's what it looks like for water to dissolve. Now, again, this wouldn't work if we didn't have this positive charge. Like if this was not an ionic thing, then we wouldn't have that interaction. We wouldn't have the bonding, and it just wouldn't dissolve. So in the instance of non-polar molecules, you're not going to get that positive negative interaction with the water. And so the non-polar substance will just remain intact. It'll just sit there and it'll never dissolve. But actually what would dissolve a grease would be a non-polar solvent. So like, for example, trying to think of a good example. Grease. Like if you had like, just think of when you're doing your dishes in the sink and you got, let's say that it was like bacon grease. You cook some bacon in a big frying pan, and afterwards you're trying to clean that frying pan and it's just got this coating of grease in there. The only way to dissolve that grease is to add a non-polar thing that can dissolve the grease. Non-polar dissolves non-polar, and then polar dissolves polar. So if you got a non-polar grease, you need a non-polar solvent. So what would you use? Soap. Soap is non-polar, and so it will dissolve it. Okay. One more point I want to make here is water has a high heat capacity. And let me just check something here because I think they might call it specific heat capacity. Yeah, okay. Let's say that a little different. Specific heat, which means it takes a lot of energy to raise water's temperature. Another way of saying this is that water is thermally stable. If you like, let's just say like you recorded the temperature, like let's say you went out to the ocean, okay, and you had a temperature probe stuck in the sand on the beach, and then you had another temperature probe 100 feet into the water. So you're taking the temperature of the water, and then you're taking the temperature of the beach, the actual beach itself. And what you were interested in is determining how much the temperature changes from day to night, okay? What you would find is that the sand would get really hot during the day, and then it would cool off at night, and you'd see these big temperature swings in the sand. But out in the water would remain very, very much the same. The temperatures would kind of stay the same day and night. And that's because water has a very high specific heat capacity, which means that it's thermally stable. It's probably going to kind of just stay the same temperature most of the time. And the book or the reading tells us that that's a very useful thing to living things. We want to remain at a stable temperature, and water helps us to do that. Okay, so this helps keep organisms at a constant temperature. So if you guys haven't picked up on the theme here, what we're trying to do is we're trying to show you why water is so essential to living things. And this is just one more reason, one more example of how water is useful to living things. So we had an example. So just to recap all of the examples of how it's useful to living things. We talked about its solvent properties, right? Its ability to dissolve things. We talked about how it's able to keep a constant temperature because of its high specific heat. We also talked about the fact that it forms a surface tension. And then up here, we talked about the fact that water sticks to itself through cohesion, and water has the ability to stick to other things through adhesion, all of which are useful to living things. Okay. And by the way, if you haven't connected this in your mind, why does water have all these additional properties? It all comes back to this main idea right here, which is that water is polar and therefore it forms hydrogen bonds with itself. Polarity allows for hydrogen bonding, right? That's kind of the main idea behind all of this. Okay, so today, let's go ahead and end the notes. Are you guys good down here? Do I need to go back? Pretty good. Okay, cool. Yeah, so today we're gonna mess with water's surface tension a little bit. And one of the ways that we're going to do this, let's go ahead and, Taylor, do you mind distributing that lab right there to each student? There's a stack of, the one on the left. Yeah, thank you.